My name is James, and it is my privilege to be giving the opening keynote for this conference. As you might know, keynotes at hardware conferences tend to fall into one of several categories. So the first category is the Moore's Law keynote, may it rest in peace. So this keynote observed that the number of transistors per unit area was getting very large, just excitingly large, and at some point in the near future, we'd have so many transistors that all of humanity would transform into some kind of being of pure computational energy. Then we would go out and colonize the stars or do whatever. But now we know that Moore's Law was really like more of a hint, and nature no longer wants to pay attention to this hint. So as a result, I couldn't get up here and give you a Moore's Law keynote. However, there is another type of keynote, which is still very good and which you do still sometimes see at hardware conferences. And that keynote is called, "I'm 200 years old, let me tell you how the industry really works." So in this keynote, a cranky old person gets up and they tell you about the industry and all the ways that it screwed them over and how they were actually integrals in the development of really important technologies. And so in this kind of keynote, you get to hear beloved stories like, "I invented transistors, but I lost the napkin that I wrote the invention on, so I can't prove anything, but just trust me, I totally did it." So these kind of keynotes are always very entertaining, but unfortunately, I can't give this kind of keynote because I'm still just a kid. Right? Basically, a kid that's being held in the arms of a strange clip art man, but he looks happy, so I feel happy. Regardless, I feel like I can't give this type of keynote about my 200 years of experience in the industry because I don't have that. So, I thought to myself, what are the other types of keynotes that you typically see at hardware conferences? So I thought, maybe I could give a keynote about quantum computing. Now, if I were to give a keynote about quantum computing, I'd probably just reuse the picture that I had in the other slide because, who knows what's happening in quantum computing? You talk to some people, they say, oh, quantum computing is great. You talk to other people, they say quantum computing is the worst idea in all of history. So, for example, I read one article by a well-known physicist. And so the article said, a useful quantum computer needs to process a set of continuous parameters that is larger than the number of particles, subatomic particles, in the universe. It is absolutely unimaginable how to keep errors under control for 10 to the 300 continuous parameters. So that maybe sounds problematic, okay? But look, I don't know. I'm not going to get up here and tell you how this stuff works. As you know, I recently got tenure, so I no longer do arithmetic, okay? I let machines take care of things. And that's why I have things bookmarked in my browser, such as how many fingers are on one hand? Or why do I have no juice after drinking all of my juice? This is what a tenured professor lifestyle looks like. So I'll leave the debates about quantum physics to the physicists. So I couldn't do a keynote on quantum physics. I couldn't do it on these other things. So what could I give the keynote on? So I thought to myself for a while, I say, there is another classic format for a keynote that I can use. And that format is a series of controversial opinions, which I mostly believe, but which I will present as if I totally believe them all. Okay? So what this allows me to do is have the freedom to say literally whatever I want, and then if I'm questioned on things, I can protect my self-confidence by saying, I didn't really believe that stuff, so let's just go to the wine bar. Okay, so all of these types of keynotes, they basically are centered around a high-level outlandish claim. And so here's my high-level outlandish claim. Hardware community, you are in crisis, right? This talk is going to be all about how I think there are important issues in the hardware community that need to be addressed, but can only be addressed by fundamentally thinking about how we build processors, right? In particular, I'm going to argue that the way that we think about ISA design is starting to fail. And those failures can be seen in three different dimensions: power consumption, security, and performance. So for example, let's look at power consumption first. So the Uptime Institute, in 2019, they issued this survey of all data center operators. And among other things, they asked people, what does your power consumption look like inside of your data center? And so one of the quotes from this report is very interesting. It said that improvements in data center facility energy efficiency have flattened out and even deteriorated slightly in the past 2 years. The average PUE for 2019 is 1.67. So what is PUE? So PUE stands for Power Usage Effectiveness. It's the total energy consumed by the data center divided by the energy that's used solely for computation. So the ideal PUE is 1. So that PUE ratio would mean that all of the consumed power is going towards CPUs and RAM and storage devices and so forth. And so PUE ratios that are higher than 1 account for data center infrastructure like cooling, lighting, uninterruptible power units, things like that. So the PUE values are not where we'd like them to be. But meanwhile, particularly the bigger data center companies are setting very aggressive goals. So for example, just 4 days ago, Microsoft announced that it will be carbon negative by 2030. Okay, so I have a few reactions to that. So first of all, okay, that's a very aggressive goal. Okay, a very positive goal, but a very aggressive goal. And second of all, do you see the backgrounds behind all those executives? There's a lush forest, and there's a set of exotic mountains. There's some kind of life-supporting moon that's standing behind Satya. So apparently all of these Microsoft executives are living inside some kind of advanced biodome where they keep Steve Ballmer in carbonite in case they run out of supplies. They have to sell some extra Windows XP licenses to make ends meet. So that's very strange. But the third thing that I noticed about this announcement is that optimistic facial expressions absorb no carbon emissions. So Microsoft isn't going to hit this goal purely through positive thinking. So if they are going to hit that goal, what does that mean? That means that people like us in the hardware community have to start thinking much more hard about how we're going to minimize the power draw for our chips. However, if we look at those survey results from the Uptime Institute, what we see is that we're actually a long way from achieving those goals. So I would say, once again, hardware community, you are in crisis. There are executives living in biodomes whose livelihoods depend on you. So we got to get it together. Now, here's another sign that your community is in crisis. As you may have noticed, over the past year, it was actually a great year to be a graphic designer because of things like Meltdown, Zombie Load, Spectre, TL Bleed, Fallout, Foreshadow, Kylo Ren's Sad Cache Syndrome. Hyperthreading technology doesn't prevent the Minecraft servers from crashing. Hardware community, you are in crisis. We've looked at these problems, and right now we're sort of in this weird place where we're not quite sure what the division of labor should be between hardware and software. So that's one of the things that I'm going to talk about in this presentation. I should also mention performance. So increasingly, I think that software developers are understanding that optimizing software performance requires hardware optimization. So if you look at things like big little architectures, where you have a bunch of high-frequency, high-voltage cores, and then a bunch of low-frequency, low-voltage cores, and you move workloads between them as necessary. So this is a great idea, right, for reducing power consumption when possible and increasing performance when necessary. But the problem here is that, as I'll discuss in more detail later, the optimal scheduling in these kinds of systems oftentimes relies on the scheduling algorithm having access to low-level microarchitectural details that are typically not exposed in today's ICEs. So let's say that you want to optimize your software-level workload. You could also try to essentially compile it down to an FPGA, right, to take advantage of these custom logic blocks to implement your algorithm directly on them. Or you could go to that ultimate level and actually create an ASIC, which is going to directly embed a very efficient implementation of your software at the hardware level. However, the problem here, I think, is that many general-purpose applications, they're actually not amenable to these kinds of pure hardware implementations, right? Okay, so not everything is scientific computing or some kind of bespoke machine learning workload. And so I don't think that we can rely on these techniques to get software performance as close to quote-unquote native hardware performance as possible. So I repeat once again, hardware community, you are in crisis. Now, luckily, like all great prophets, I have come here with the message of doom, but also a message of hope. And so in the rest of the keynote, I hope to provide you with the potential solution to all of these problems that I've mentioned. So fundamentally, this talk is about opening up the microarchitecture. So to be clear, I want to preserve the performance benefits that the community has fought so hard to get from deeply pipelined out-of-order processors. Okay, so as I'll explain later, what I'm going to propose is different than things like, let's say, transport-triggered architectures or raw machines or things like that, which essentially forsake all these types of things. So I want to preserve these deeply pipelined out-of-order processors. However, I also want software to be able to introspect and configure the microarchitecture. And I want software to be able to do this for the purposes of improving security, decreasing power usage, and improving performance. So I think that we can understand some of my proposals better if we think about what happened to the networking people about 10 or 15 years ago. So back in the year 2000, you can imagine that someone would have gone to a networking conference and said, networking community, you are in crisis. Right? And if you want to know more about this particular crisis that they suffered, I recommend taking a look at this paper called The Road to SDN, an intellectual history of programmable networks. Okay, and so this paper does a really nice job of describing the challenges that that community was facing approximately 15, 20 years ago. So what were those challenges? Well, let me give you a small example to motivate. So imagine that we've got some network element here. It's a switch or a router. And then imagine that a packet comes in. So how is that switch or router going to figure out what to do with that packet? Well, it's going to inspect some local routing state. Okay, so basically, that routing state is going to have a series of rules. So for example, if the packet should go to Bob, we're going to forward the packet out over port 1. If it should go to Charlie, maybe we need to broadcast it to all ports. And if it's from David, well, maybe we think that David sucks, so we're just going to drop the packet. No packets for David. It's too bad that he's David. So we've got that routing table there, and we're going to call that the data plane. Okay? Now, in addition to the data plane, what you also have is this thing called the control plane. So think of the control plane as the brains of the network. The control plane is the thing that's determining how that data plane state gets set. So if we look at a bigger network consisting of multiple computers connected to a switch, and then each switch or router talking to multiple other switches or routers, what do we see? Well, in the early 2000s, there was typically a distributed consensus algorithm that was run to manage the data plane state. In other words, each one of these forwarding elements, the switches or routers, would essentially exchange a bunch of packets. And through the process of exchanging those packets, those networking elements would hopefully converge on some globally optimal definition for what forwarding state should look like. Now, what I just described seemed very nice, almost like British tea time. How delightful. Why not just have a bunch of participants exchange messages and then everything should hopefully work out? Of course, any of you who've actually worked with distributed systems know that distributed systems is not tea time. It's basically a fight at a British soccer pub. Okay? Anything that can go wrong will go wrong. And so as it turns out, this approach for managing the data plane state was not working out too well for people. So what were the problems people were seeing? Well, there was poor scalability because getting the network as a whole to consent on anything required a lot of messages being exchanged. There was actually weak convergence too, because network elements can drop things, reorder things, so on and so forth. And so it was very difficult at any given moment in time for the aggregate snapshot of data plane state to actually reflect anything that was consistent. And so this lack of consistency caused low robustness, right? You couldn't trust the network very much because you weren't guaranteed that the network would be in a coherent state. And then there was another set of problems. So let's say that we look at one of these individual switches. Well, back in the early 2000s, these network devices, they actually were vertically integrated with a bunch of very complex protocols. So on any individual switch, you might see BGP protocol running, OSPF, quality of service protocols that guarantee some type of latency between different nodes, network address translation, firewall, so on and so forth. So what did this particular characteristic mean? What this meant is that let's say I just give you the data plane state for a particular element. Well, it's actually hard to figure out how all that state got there. Was a particular entry set by BGP? Was it set by firewalls? Who knows? So what was the insight behind SDN? Well, one of the insights is that you want to centralize the control plane. So logically speaking, you have a single controller who is going to be able to talk to all of the forwarding elements out there. And so that controller is going to be able to act as a single centralized point by which all of the data plane state is configured. And so this gets rid of a lot of the problems of robustness that come about if you force everything to be distributed. Now, the second idea behind SDNs is that you want to make these forwarding elements programmable. Roughly speaking, at each one of these elements, you want to have a series of match action APIs. such that the centralized controller can essentially install rules, where each rule says, hey, if a packet satisfies this particular set of characteristics, if its header looks like this, or if it's from or going to particular entities, then you should do a particular action. Forward it, drop it, broadcast it, so on and so forth. And so the reason why this was nice is that now that centralized SDN controller could now be that single party that sort of understands how all these protocols work. So it could be that centralized controller who understands the details of BGP, quality of service, network address translation, and so forth. Roughly speaking, all of these things can run as libraries, and the individual switches don't have to worry about this. They only have to worry about accepting these rules. Okay, so I give you that background to help motivate what I'm about to say in the remaining 30 minutes or so about hardware microarchitecture. So I'd like to go to the future, right? So with the history of SDNs in mind, what I want to do is talk about what the ISA of the future should look like. Now, of course, I realize that making predictions about the future is notoriously difficult. So as a concrete example of that, let's consider the Paris World Exhibition of 1900. So at this event, a bunch of artists were asked to envision what life would look like 100 years in the future, in the year 2000. And the results were, not completely accurate. So for example, in the year 2000, both criminals and police officers were assumed to be flying constantly. In the year 2000, people were also predicted to be attaching buses to whales. And after you rode that whale bus to some destination, people were predicted to start flying again, and then for unclear reasons, they would go to eagles' nests and then try to steal eagle babies. Okay? So in the year 1900, this is what people thought we'd be doing essentially right now. Of course, with the benefit of hindsight, we now know that 100% of the people who try to fly using wings attached to their ankles are dead, completely dead. All the people who tried to attach buses to whales, they're dead because they were killed by whales, okay? And all the people who tried to fly using pillowcases and steal eagle children, they're dead and their bodies were eaten by baby eagles, okay? So I just say this because I want you to understand, I understand that prediction is fraught with peril. But I'm an American and I lead by example, so I try to do it nonetheless. So, what should the contract between hardware and software look like? Well, traditionally, it looks something sort of like this. We have the ISA level, okay, and this is sort of the domain of developers and compilers. And then here, we have microcode, and then we have the microarchitecture, loosely speaking, which I'll define as the wires, the functional units for computation, the memory units, all the power management stuff. We also have some microcontrollers. So for example, some chips have microcontrollers to manage power. You can imagine microcontrollers might exist to interact with some types of I/O devices. But traditionally, all of this stuff, the microcode and all of the basically micro asterisk stuff, that was all the domain of the hardware vendors. And then beneath that, of course, we have physics. And then beneath that, we have metaphysics, which describes why we have more electrons than positrons and what Schrodinger's cat really means and so on and so forth. And so this layer, of course, is controlled by Cthulhu, as everyone here should know. Cthulhu, of course, cannot be stopped. He is destined to rise, and that will never be prevented. A great eclipse will cover the sky. The street will be filled with those who tremble in terror at his might. Great towers will be constructed in his honor. And I'm very sorry. These slides were actually meant for a different presentation. I'm going to be presenting later to the EU Business Association on GDPR compliance. Fun and easy. So feel free to talk to me later if you want to talk about how Cthulhu can be harnessed to send email to people about how their privacy preferences might need to change. Anyways, I digress. So we're talking about the contract between hardware and software. So this is what it looks like right now. And so what I want to do is actually create a new layer here, okay, that has sort of three pieces. So let me step through those three pieces. Right? And what we're going to do by introducing these new pieces is actually expand the scope of what developers and compilers can do when they want to interact with hardware. So what's that first piece there? So that first piece is the discoverability and programmability API. So by discoverability, I mean that I want chips to be able to describe their microarchitectural features in a machine-readable way. And I'll give you specific examples of this later on. But I think that having this ability will actually enable interesting new types of compiler optimization, because now as compiler writers, we don't have to try to optimize for a particular architecture by reading some dense optimization manual. And I think it actually enables new kinds of JITting, which I'll describe later as I mentioned. The second thing that we want to have is we want to have an open format for the microcode. So traditionally, the way that microcode works right now is that it is closed source, it's proprietary, it's encrypted, in fact. So you can't really even see what the plain text microcode is. As I'll argue, particularly for security, I think this is very, very bad. And so I think that what a chip of the future should do is actually provide an open format microcode so that individual software developers can verify what vendor-provided microcode updates are doing. And also, we can actually come up with new ideas for how we might leverage microcode to improve the performance or other aspects of our processors. And then finally, I want to have a programmability API for microcontrollers. This is for things like the power control units that many processors have. And I think that opening these things up is actually going to, once again, allow us to really unlock a lot of low-level performance and power benefits that really can't be done right now if we keep all of this stuff proprietary. So what do I call all this stuff? Well, for all of you graduate students in the audience, as you may know, 90% of research is coming up with a cool name for your research project. So I call this software-defined microarchitecture. And I've written it in green so that you know what the important parts are. So this is what I will be talking about today, and I'm going to use some case studies from recent history to sort of motivate and explain where software-defined microarchitectures might have helped us solve some problems. So first we're going to talk about security, okay? And what we're going to do is we're going to talk about SGX. So I want everybody to prepare yourselves, okay? SGX, let's do this. There's a lot going on in SGX. As you may know, I'm going to present some of the details, but try not to get confused by all the things that are happening with SGX. I'll give you a high-level overview. If you want to talk about SGX in more detail later, do not find me after the talk. So at a high level, how does SGX work? So we've got our standard stuff that we see in a CPU. We've got the core itself. We've got our caches. We've got CR3, the page table pointer. And we've also got the TLBs. So SGX is going to add a new privilege bit, essentially, is enclave. It's going to add some other stuff, which I'll show in the course of the next couple slides. So imagine we've got physical RAM sitting there in the middle. SGX is going to add something called the memory encryption engine. So what does this thing do? Well, basically, the memory encryption engine is going to separate physical RAM into normal system memory. That's the normal memory that we all know and love. And a region called the enclave page cache. So this is where we're going to store the memory state for these sensitive computations, or enclaves in SGX parlance. And so the memory encryption engine is going to add rollback counters, message authentication codes, and encryption to outgoing memory writes to the EPC. So in other words, when an enclave writes something to a sensitive memory page, the memory engine transparently protects it using cryptography. And similarly, when enclave code is running and it tries to read memory from one of these protected regions, the memory encryption engine is going to transparently decrypt it, make sure that there's been no rollback that's happened, and also make sure that the integrity has not been tampered with. Now, up to the right, we see this thing called the enclave page cache map. So this is a new SGX structure. You can essentially think of it as an inverted page table. It contains one metadata entry for each page in that EPC region down at the bottom of the RAM picture. And so the EPCM can only be modified by SGX instructions, and is consulted during memory accesses to prevent non-enclave code from accessing EPC pages. And so it's got a bunch of bits up there, like a valid bit saying, is this particular EPC page actually bound to running SGX enclave? If so, what is the enclave ID? So on and so forth. And so let me give you a very sort of a quick and high-level overview of how you create an enclave. So before you call this ecreate instruction, this is the thing that kicks off the initialization process, you've got the plain text code and data for the initial enclave content sitting up there somewhere in normal system memory. Now, when you call this ecreate instruction, basically what it does is that you're going to pass it the address of an initialization page for the enclave. The instruction is going to copy that into the EPC memory somewhere, right? And this is going to basically tell SGX, hey, I'm starting to create an enclave. And so if we look in the upper right of the EPCM, we see that one of those entries has become blue, which means that now we've got one of these EPC pages has now been allocated to an enclave page. In this case, it's called a SECS page, a SGX enclave control page. So then you might want to try to add a regular page, right? A page that might just belong to regular code or data for the enclave. You do that with the EADD instruction. Once again, you copy a page from untrusted system memory into the EPC. You can see in the upper right, we've marked another EPCM entry as used. So now this enclave has 2 pages associated with it. You then have to call eExtend. So what eExtend is going to do is every time you call eExtend, it essentially is going to update a cumulative hash of all of the data that you're putting into this enclave, right? So this cumulative hash is going to be used for attestation later on, if you're familiar with that. Attestation is basically a technique by which a remote server can prove to a client the software that it has loaded into memory. And the proof typically takes the form of a cumulative hash over all the code and data that's been loaded into the enclave. So you do this a couple times. You'll see we've done a bunch of EADDs and eExtends. If you look at the EPC, now you see that we have a bunch of pages added there. Then we do einit. Einit basically tells hardware, hey, the enclave is created. No more updates to this enclave are allowed. So how do we do memory access checks in SGX? So SGX basically adds some extra hardware to ensure that those EPC pages can only be accessed by enclave code. And those checks rely on that EPCM data structure that I showed you before. So roughly speaking, if you dig through various manuals about how this works, the flowchart looks like this. So an enclave computation generates a virtual address. We check to see if that address is mapped to an enclave region. If the answer is yes, then we essentially go through the EPCM. We make sure that the appropriate enclave is actually accessing a page that belongs to that enclave. We check that the operating system, who is not trusted in SGX, has actually performed the correct mapping from a virtual address to physical address. And if all that works, then we allow the memory access to succeed. Otherwise, we don't allow the read or the write to actually tamper with enclave memory. So, okay, why is this relevant? I just wanted to motivate I wanted to explain how SGX works at a high level to motivate some of the security problems, right? So one of the security problems is that SGX is vulnerable to hyperthreading side channels via the functional units. So if you look at this delightfully colorful pipeline diagram here, what do we see? So we see a single physical processor that has 2 logical processors. Okay, so we see sort of the front end part of the processor implements the logical CPU abstraction, but then in the middle we have things like the functional units and the register reads and stuff like that. All of that is shared by the 2 different logical threads of computation, here colored yellow and blue. And so imagine that we had enclave code running on one of these logical CPUs and that we had a non-enclave code running on the other one. Well, what you'll see is that there's actually a contention. Right? If we look at, for example, the functional units, the execute stage, then those execute units are actually shared by enclave code and non-enclave code. So that's kind of a bummer, right? And there's another bummer too, which is that SGX is vulnerable to cache-based side channels. And so if you're interested in this kind of stuff, you can see papers like the Foreshadow paper. So at a high level, what that paper describes is that there's out-of-order execution in all modern processors. And due to that out-of-order execution, there's actually race conditions between a memory value being read into the cache and being computed on. So there's a race condition between those operations and the permission checks on whether those memory accesses should have been allowed in the first place. And so why is this a problem? Well, in the enclave computation model, there's an untrusted host, an untrusted virtual address space that's going to embed the enclave computation, right? So that means that in a single address space, there's both a trusted enclave code, trusted enclave data, which can only be accessed when the CPU is in enclave mode, or so we would hope. But then there's also this untrusted host code and untrusted host data. And so what can happen is that the untrusted host can load an enclave. It can wait for the enclave to bring a clear text secret byte into the L1 cache, and then it can leverage sort of meltdown style probe array tricks to try to read the value of the byte. And so at a very high level, this is a figure from the foreshadow paper. The details are not super important, but essentially what this shows sort of a speculative attack that tries to read kernel memory, but the basic idea is the same for reading memory from an SGX thing. So basically you flush out the memory from the cache that belongs to some, what they call oracle line. Then you try to do a move up at the top. You basically try to do a memory access that is dependent on some secret piece of data that you, the entrusted code, should not be able to access. Now, as you see off on the left, there's this out-of-order execution window, right? During this time, those instructions in yellow may be executing. They may be racing with the privilege checks, with the access permission checks for that memory access. And so essentially, depending on who wins the race, if the race is actually won by this code here and we're able to access that secret memory location before the privilege checks come in, well, the code on the left can't actually read that data at the ISA level, at the architectural level. But you can essentially use standards like prime plus probe attacks and things like that to read what the secret value was. So there were all kinds of attacks that happened to SGX over the past 2 years involving this kind of stuff. And so the basic sort of summary of the past 2 years for Intel is something like this, okay? There's just a series of just devastating press releases, and I certainly hope that the Intel PR people have been given some nice vacations. So what happened with this stuff? Well, among other things, there were some microcode patches that were that were issued. And so you can go to the Intel webpage and look at what these patches do. So for example, this is a patch for some of the foreshadow type stuff. Among other things, the patch modifies some operations to implicitly remove data from the L1 data cache during certain privilege transitions. So what's an example of those privilege transitions? Well, something like an enclave exit, right? So what you want to happen is when the core transitions out of enclave execution mode, you basically no longer allow enclave secret data to reside in that L1 data cache. So with these microcode updates, the Intel SGX attestation will also indicate whether hyperthreading has been enabled by the BIOS or not. So remember, hyperthreading is also another venue for these side channels. So why is the SGX attestation important? Well, this is important because it basically allows the remote party, the thing that's talking to the enclave, to decide whether or not it wants to trust an enclave that's running on a CPU with hyperthreading enabled. So that's kind of interesting, although that kind of kicks the can down the road, right? So this doesn't really fix the problem so much as it says, let's expose the problem to the remote client and then let the client figure out what to do. Okay, so what would I say that the sort of problems are here that an open microarchitecture might address? So the first problem is the microcode format is proprietary, patches are encrypted. We don't really know what's going on with these things. So we get these sort of text-level descriptions of stuff, but fundamentally it's hard for us to verify what's going on. And second of all, the microarchitecture itself is actually kind of gray box. And so what this means is that as security researchers, we're kind of flying blind here, right? So we don't fully understand the impacts of the microcode or the fundamental sort of security properties of the underlying microarchitecture. And just to be clear, I do know that Intel and other companies publish things like the optimization reference manuals. So you can look in these manuals and you can see very exciting figures like this. You can also find text about various sort of microarchitectural level behaviors of the CPU, okay? However, I should note that this kind of text, this is not machine readable, right? Nor is it machine verifiable. We don't know what's being left in, what's being left out. So for example, if you look at a lot of these microarchitectural optimization manuals, you don't see a whole lot about SGX. You don't see a whole lot about VMX, okay? So as security people, this should make you a little bit uncomfortable. And so if we go back to the foreshadow paper, the foreshadow paper actually has some really interesting observations here. So it said, quote, "We want to emphasize that foreshadow exploits a microarchitectural implementation bug and does not in any way undermine the architectural design of the Intel SGX and Ts in general. However, an important lesson from the recent wave of transit execution attacks, including Spectre, Meltdown, and Foreshadow, is that current processors exceed our levels of understanding." So when I read that last sentence, I got chills. I mean, I didn't get actual chills because I'm very sort of like not afraid of these things, but like I could imagine that a weaker person with a sort of softer constitution might have gotten chills, right? That's pretty crazy. right? That we can't really fully understand the security properties of our processors because we don't have enough details to completely understand them. So, getting back to my idea of software-defined microarchitectures, what might my Christmas list be? What features might I want given these problems with SGX that I just discussed? So one thing that I would like is to have unencrypted open format microcode. So the reason why this is helpful is because it lets third parties verify the correctness of patches that are issued by vendors. Now I should note that patches still need to be signed. We don't trust anyone, right? Or at least you shouldn't. So we don't want arbitrary people to be able to issue microcode patches. We probably want to limit it to just the hardware vendors themselves and then maybe like operating systems vendors too, okay? So we still want that protection that comes from signing, but I argue that the encryption aspect of it is actually making security verification more difficult to perform. I'd also like discoverable microarchitectural details. As I've alluded to in prior slides, I'd like a CPU to be able to export a machine-readable description of the microarchitecture. And once again, I do know that there are these optimization reference manuals out there, but these things are not machine-readable. Okay, what I want to be able to do is take these microarchitectural descriptions and feed them into formal tools, right, to guarantee things about how the processor works. And so if we had these machine-readable descriptions of the microarchitecture, this would allow developers to be able to reason about the security properties of the microarchitecture and also the security implications of microcode patches that ostensibly fix some feature. Another nice thing about having CPUs that sort of export these discoverable details is that it kind of enables these dynamic automated JIT-style approaches to creating CPU-specific code. As I'll talk a little bit later on when I talk about compilers, one thing that a software-defined microarchitecture does is that if you want to take advantage of it fully, you have to have a compiler that actually targets it, right? And so creating a compiler that targets a software-defined microarchitecture, if we have to do everything by hand, if we have to do it manually, that seems very tedious. These machine-readable description, I think, will allow us to use automated or semi-automated tools like program synthesis to help us lower the burden of implementing these compilers. So the other thing that I'd like is customizable or at least open algorithms for things that manipulate parts of the microarchitecture. So mapping virtual addresses to cache lines, mapping virtual addresses to TLBs or to BDB entries, so on and so forth. Some of this stuff we know because the vendors have told us directly. Some of it we think we know because we've inferred it, but I'd actually like to know sort of with complete confidence. Once again, I think this will help us reason about security. So that's my Christmas list, at least with respect to security. But a natural question arises. So why would hardware vendors give away these secrets? So in a standard processor, things like microcode formats, low-level microarchitectural details, they're proprietary for a reason. Hardware vendors want to maintain tight control over who can modify the processor to maintain a consistent high-quality experience. And hardware vendors also want to prevent their competitors from learning trade secrets. So all of this is true for current commodity processors. However, I'd argue that the goal of research isn't necessarily to make current hardware vendors happy. So the goal is to point out new ideas that may be disruptive in some good ways. So yes, I just want to be open about the fact I understand that Intel and AMD and so on and so forth might not be happy with this proposal for software-defined microarchitectures. So I think that's okay if they get a little bit upset. Now that being said, I am a professor, so I'm always looking for grant money. So Intel and AMD and Samsung, if you're listening, I'm ready to be sponsored. I'll drop this idea immediately, okay? I'll wear that jacket wherever you want that jacket to be worn. For example, you want me to wear that jacket at a wedding, I will wear that jacket at a wedding. If you want, I'll wear it at a funeral. The funeral package costs you extra. Everything is negotiable, though, so just name a price. We'll make it work out. For example, if you want me to wear that jacket at the birth of my firstborn child, it's done. I'll do it, okay? What better way to bring a new baby into the world than by giving them a demonstration of the horrors that American professors have to go through to get funding for their graduate students? So anyways, let's shift gears now, and let's talk about a different topic. So let's talk about power consumption. So we know that if we do a poor job of managing power, then our chips will melt and customers become unhappy because the customers did not intend to buy melted processors. However, there's a tension. Right? So customers don't want their processors to melt, but they do want frequencies to be high, right, as often as possible in order to make their workloads complete faster. But they also don't want to consume too much power. So in this part of the talk, I'll sort of discuss how software-defined microarchitectures can manage power consumption. However, before I talk about that, it might be useful to discuss how current state-of-the-art processors currently manage power consumption. So for example, if we look at Intel Skylake, that microarchitecture introduced a couple of new mechanisms for saving power. So if we consider AVX instructions, which are basically SIMD instructions, AVX execution units are now power-gated. Right? And this is because most applications don't use AVX instructions. So they can kind of be powered down and kept in a low voltage state in the common case that they won't be used. So that's pretty cool. Skylake also introduced something called the package control unit, the PCU. So that's a microcontroller, that little, I guess it's magenta thing in the middle of the diagram, that is going to inspect processor utilization and dynamically modulate the frequencies and the voltage inside. These are what are traditionally been called P states. So there's a low-range algorithm that essentially tries to minimize energy consumption. Sorry, there's a little typo there, when utilization is low. And then there's a high-range algorithm that's going to run when utilization is higher, that's going to try to maximize performance. So the OS can tweak some of the parameters for the algorithms here. But the problem, I would argue, is that the CPU doesn't expose a full set of microarchitectural power events and knobs via the ISA. And I think that actually prevents a lot of very powerful optimizations for lowering energy consumption. So there have been a couple of research papers that have described the types of optimizations you might be able to do if you had an open microarchitecture. So for example, there's this cool thread motion paper. And the observation in this paper is that microarchitectural events actually impact power consumption. But to take advantage of these events, the policy engine that manages power needs to be able to see those microarchitectural events. So for example, imagine that you have time on the x-axis and the activity, the amount of compute pressure that two threads are giving to the processor. You can imagine that one thread is running on a high voltage, a high frequency chip, and it experiences a cache miss. So what you might want to do is you might want to immediately transition that core down to a low frequency core as it waits for the cache miss to finish. And then meanwhile, you might want to cycle up the previously low voltage thread to a high voltage one. However, there's a problem with doing this in the traditional approach. And that problem is that on standard microarchitectures, that transition delay is oftentimes in the order of tens of microseconds. So what the thread motion paper says is basically, okay, let's imagine you had one CPU that's always sort of low voltage and low frequency, and then you had another CPU that's always high voltage, high frequency. So each one of those CPUs has registers, each one runs a thread, but there's also going to be a series of microarchitectural status registers that track a series of very low-level events like cache misses and things like this. And they're all going to be hooked up to the PCU, the power unit that controls stuff like voltage. So if you have a cache miss on the high VF CPU, that's going to trigger the thread motion. So essentially this means that we're going to take the register state on those two CPUs, we're going to swap them. And so what's nice about this is that thread motion can occur at nanosecond scale, right? Because we're not actually doing voltage transitions between the two CPUs, we're just swapping register state. So that's pretty cool. Now the problem though is that the PCU, not the developer-provided microcode, actually manages that transition process. So you can imagine that in a software-defined microarchitecture CPU, what you would want is to expose access to those microarchitectural registers that involve power. And you'd also want to expose microarchitectural access to the registers that sort of track stall triggers. So these are things like cache misses, floating point activity, maybe there's a page table walk that has to take place due to a TLB miss. So we want to expose all of those things to a programmable PCU, right, to something that the software can actually update. And if you can do this, then you can imagine that you could have a sort of arbitrary software-defined mechanisms to implement things like thread motion. As another idea, you could try to do something like very fast voltage boosting to improve the tail latency of applications. So what do I mean by tail latency? So imagine you've got a web browser here, and it's going to talk to some web service off to the right. So typically the way that these things work is that a single request involves something called a partition aggregate model. The request comes into the front end. That single request then generates a bunch of additional ones to workers. Those workers send some reads and some writes to storage devices, and then we see a bunch of responses coming back up this tree where they're sort of collated and combined, and eventually a single response is sent back up to the client. And so the thing to note about this partition aggregate model is that the overall response latency is dominated by stragglers, right? So if 99 of these workers are fast, but one of them is slow, then it's that one slow worker that determines how quickly the overall thing finishes. So there's this pretty cool paper called Adrenaline, which basically says, hey, why don't we try to do voltage boosting, but just for the queries that impact tail latencies? And so like as a specific example, think about memcached. So memcached is a very popular in-memory key value store. And it's often placed in front of slow databases or storage services to cache results. And it essentially implements a very simple API. I want to set a particular key value pair. I want to get the value associated with the key. I want to delete a key. So you can imagine, or not have to imagine, this is just true, low latency memcached responses are critical for modern web services. So what the Adrenaline paper shows is a bunch of latency profiles for a bunch of different operations. So we see the gets, the sets, and the deletes. The x-axis is latency in microseconds, and so we're looking at CDFs. And so what we see is that the median latencies for gets is roughly speaking about 3 microseconds. So each one of those lines is a different processor frequency. We see that the median latencies for deletes are a little bit worse, but there's still not too much of a long tail. But here if we look at sets, what we see is that we see much higher median latencies and also much longer long tails. So what might we do here? Hello there, mortal. I have a message for you. And that message is only boost requests that would decrease tail latency. So Thor did not actually write this paper. That was just me ad-libbing right there. But this is the basic idea here. The basic idea is that you only want to provide the voltage boost to things that would decrease that tail. So if you look at a workload of no boosting, time goes off to the right. Imagine that you had this series of operations: 2 gets, a set, a delete, and then another set. So traditional DVFS would just boost that entire sequence. But as it turns out, only the sets are the ones that are actually amenable to boosting. And for the other ones, you're just basically wasting extra voltage. So what an Adrenaline-style approach would do is that it would only boost the sets there. And so what that would do is give you a similar reduction in tail latency, but preserve power consumption. And so how does Adrenaline do this in practice? Well, it leverages 2 ideas. The first thing it leverages is this thing called short-stop. At a high level, short-stop is basically a dual voltage system. So you essentially have like a voltage high, a voltage low, and then a voltage boost, which allows you to transition to the voltage high more quickly. For those of you who like diagrams that presenters don't give you enough time to process, here one is. Go look up at the paper. But the basic idea is that using this architecture, short-stop has nanosecond latency of voltage transitions, and the cost is about 10 to 16% extra area cost. So this is what Adrenaline is going to use to sort of switch rapidly between different voltage levels. And the second idea, which is actually sort of the core one with respect to software-defined microarchitectures, is that Adrenaline is going to observe and respond to program behavior. So at a high level, a request comes in from the cloud. That request comes into a query identifier. That's all at the software layer. That query identifier is going to look for sort of characteristics of the query that would make it amenable or non-amenable to voltage boosting. So for example, the type of memcached request. The decision engine then decides whether or not the CPU should be boosted or not, and then we hand off the decision to short-stop, which is then going to make a decision to change frequency levels or not. So with respect to these types of optimizations, what is my wish list for software-defined microarchitectures? So once again, I want discoverable microarchitectural details, right? This time about thermal and power behaviors. So for example, I want to know the mappings from microarchitectural components to voltage domains. I also want to have access at the software level to per component counters for things like thermal statistics, the power draw, any type of microarchitectural events that are going to impact potentially power decisions. So things like cache misses, page table walks, stuff like that. So in the discussion of security, just to contrast this, I asked for processors to describe sort of their functional behavior in terms of, how many functional units they have and stuff like that. What are the latencies there? Here I'm asking for the processor to describe the power profiles and the thermal limits. And I'd also like the ability for software to be able to define a fine-grained developer-specified power policies. So the PCU should be programmable, and furthermore, it should have access to all those microarchitectural counters that I mentioned above, but also to maybe a subset, maybe the whole thing, but to some piece of ISA-level state. So why is access to the ISA-level state important for these microcontrollers? Because if you want to do things like adrenaline, right, where is the request type for a memcached request going to live? It's going to live somewhere in packet data that's been copied into memory, maybe moved into a register. So we want to make sure that those things are accessible to the PCU as well. So I should note that I have a very high emotional IQ, and using that very high emotional IQ, I've detected a possible objection to software-controlled power management, which is basically that software doesn't work. So software is buggy, it's incorrect all the time. Why would we want to put this in charge of power? So for example, as you may have heard, Microsoft has been issuing a series of cripplingly bad software updates for Windows 10 that are just like wedging machines in some cases, that we're just trying to install these updates, trying to fix stuff. And as like a personal story of woe, this is completely true. I have a Windows 10 laptop right here. I installed a recent update, and then I just wanted to click on something. It's a PDF file, it exists to be clicked on, so I took the mouse and I clicked the bejesus out of this thing, and literally nothing happened after I installed the update. Nothing happened good, nothing happened bad. And so this is like a very deep question of metaphysics, kind of like when cats try to understand the causality of like plastic wrap, right? So you look at this poor cat, and it's kind of like me trying to click on that icon, right? The cat's saying, well, this air is solid. This makes no sense. And by the way, if you look in this picture, also notice that this is not an actual cat here. This, to me, is the most devastating part of this picture here. The plastic wrap is one thing, but there's some psychopath who put a cat-shaped stone in a place where a cat would obviously find it. This is the sick world that we live in. So anyways, if we look at SDNs overall, I would say that SDNs overall appear to be a win, right? So you will find some papers about how do we debug SDN infrastructure. But overall, people seem to enjoy the fact that they have more programmability now. So I point to this stuff to say that yes, it is true that if we make some of these things software controlled, then there might be some problems with the software itself. However, it seems at least in the networking community, people are still comfortable with the choice of going towards SDNs. And so before I conclude, I want to briefly mention a couple things that software-defined microarchitectures are not. So they are not transport-triggered architectures. So in a transport-triggered architecture, the programmer has direct control over the transport buses. So a single transport-triggered architecture instruction basically contains multiple move commands. So the way to think of it is that if you have in that commented line of code up there a traditional addition instruction, so you take R1 and R2, you add them and you move them to R3, then in a TTA architecture, what you'll see is you'll see a move of R1 to the triggering register of the add ALU. And then you'll see R2 being moved to the operand register of the add ALU. And then you'll see the result register of that add ALU be sent to R3. And so you end up getting an architecture that kind of looks like this, right? So you have a bunch of units that have these trigger registers and these operand registers, and they output to result registers. And in an architecture like this, timing and hazards must be handled by the programmer. And so what are the advantages of this? So the advantages of this are that harder level parallelism is explicit and controllable. And instruction decoding is actually very simple because basically there's just move. So it's not too hard to figure out how to handle that kind of stuff. And you can also do some pretty cool tricks by eliminating intermediate writes to the register file. And you can do that using a technique called software bypassing. So the basic idea is you have something like this, there's two add instructions, R1 plus R2 goes to R3, and then R3 plus R4 goes to R5. Then roughly speaking, you can, not even roughly speaking, this is exactly what happens, you can take the result of that first add instruction and just assign it directly into the ALU for that next sub operation without having to go through any intermediate register writes. So the disadvantages of this approach, though, are that the timing and the hazards must be handled by the programmers I mentioned earlier. And I would argue that CPUs for general-purpose software must be deeply pipelined and speculate aggressively. And the reason for that is because there's all kinds of sources for stalls, branch restrictions, things like that. So asking the programmer, the compiler, to try to sort of think about all these various ways that the timing hazards and data dependencies can arise, I don't think that's feasible. And furthermore, programmers must also handle context switches. And this is actually pretty difficult to do because there's this large amount of low-level state which the programmer has to think about. So as I mentioned at the beginning of the talk, I don't want to abandon these deeply pipelined, highly speculative pipelines that we have. I just want to make them more open and more programmable. And so I think there's actually a lot of differences between TTA and what we're doing, also raw machines, if you've heard of those things. They look very similar at a high level to transport-triggered architectures. They don't really take advantage of sort of the behavioral patterns that we see in general-purpose software. So in conclusion, what have I talked about today? Well, I've described a new way to structure the contract between software and hardware. So in particular, I've defined a new approach called software-defined microarchitecture. So in this approach, we're going to create a new layer of abstractions between the ISA and the parts of the hardware that have traditionally been managed by hardware vendors. So in a software-defined microarchitecture, we're going to have an unencrypted, open format, but still signed microcode. And we're going to do this so that developers can understand the functionality of patches that were supplied by a hardware vendor or by an operating system vendor. We're also going to have discoverable microarchitectural details about things like pipeline layout, other microarchitectural data structures like the caches or the BTB, and we're going to have discoverable details about thermal behaviors and power behaviors. We're also going to have customizable or at least open algorithms for updating the microarchitectural data structures. This, once again, is important, I think, for us, security and for performance and for power consumption. And finally, we're going to have programmable microcontrollers, right, that have access to at least some subset of ISA-level state. And so the PCU, the power units that you see on commodity chips, are a great example of this, but I think that in general, any kind of hardware accelerators or anything else like that would be amenable to this programmable approach. And so with that, I'd like to thank you for your time, and I'd be glad to take any questions.